Alright, today I will explain how to simulate simple random walks using Spreadsheet. Here I use Google Sheets, but I'm pretty sure that you can do more or less the same thing using Microsoft Excel or any other spreadsheet softwares. So let's start. First, I, I, I will simulate a very simple random walk that can go either positive one, a negative one, randomly, and along discrete time step. Okay, so this is time. Let's make it start from 0, and let's use the sequence function. Let's make it bigger. Sequence function up to there are 1000 rows by default, so that's 99. Let's put 998, so we can have the sequence starting from 1 to 998 here, but let's add 10,000 rows here. Okay, and make it 10,000. Okay, next let's generate random numbers. For the reason I will explain later, let's put this 0.5 first, and let's put use rand function. So this function generates a random number. Every time it is called, it generates a random number between 0 inclusive and 1 exclusive. Okay, we copy this function to the rest of the rows in this column. So here, so each cell here contains the same expression, but they show different numbers because every time it's called, this function rand is called, they return a different number. Okay, so, and one step, this is either positive 1 or negative 1. So we choose either positive 1 or negative 1 randomly with this probability, that is 0.5. Okay, that can be done by using this if function. So if this random number in this cell is less than 0.5, in this case that we want to make it up as a parameter, so be 2 cell. So this 0.5 is saved in this cell. So if the random number is less than this number, we want positive 1, otherwise negative 1. Okay, and we do the same thing for the rest of the rows. Okay, but each row refers to this different random number. Okay, so here it refers to B3, here it refers to B4, B5. Here you can see the expression here, and so on. So this is the step at each time point. Now the position of the random walk starts from 0. Okay, 0, the origin at time 0. And the next position is determined from the previous position plus the current step. Okay, so that in this case it would be D2 plus C3. And we copy this expression to the rest of the rows here. Okay, so the next one is determined from D3 and C4, and D4 and C5, as you can see here. Okay, so every time we edit this file, I type delete here in this cell. You can see the numbers change, right? So basically this is it. But just to make it easier to understand, let's visualize this. So let's choose these 2 columns, and let's take this graph, insert graph. Yeah, so this is it. So this is position versus time. So the horizontal axis is time, so this column A, and the vertical axis is the position here, the column D. So this is the trajectory of this random walk. It's a sample path. So let's change the random seeds. We get a different sample. Again, and different sample, different sample, different sample. Okay, we can calculate some of the statistics of this path. For example, the average position can be calculated by using this average function from D2 to the rest of the rows. So this is the average position. And similarly, the standard deviation can be calculated by using stdev function. So D2. So this is the standard deviation. Okay, so they change. These values are different for different paths. It might sound strange because theoretically, if you analytically calculate the average position, it should converge to 0. But since this is a finite sample, it may deviate from 0 by a large amount, actually. And this standard deviation will diverge as the time goes to infinity. But if we divide this by square root of the number of time steps, then it should converge to some value. But since this is finite sample, so it does not actually converge to a single value. So, but it will fluctuate like this. So far, we have been dealing with symmetric random walk, but we can make it as non-symmetric by changing this value to something other than 0.5. Let's make it 0.48, for example. Oh, no, not this one. 0.45, suppose. This is highly biased towards the negative side because the probability of choosing positive 1 is 45%. So accordingly, the probability of choosing negative 1 is 0.55. So there is 10% difference in the probability, so it's highly biased towards the negative side. Let's make it 0.48. It's less biased, but still biased, as you can see. So let's make it 0.52. Now it's positively biased. Like this. Okay. So that's it.